Welcome to my video on the scalar or dot product. This is introduction to vectors number 5. The link to number 4 is at the back of this video and the final slide. And in this video I'm going to talk about the scalar or dot or inner product. You're going to see those terms used interchangeably in mathematics and physics. So just kind of keep that in mind. That different authors or different teachers will show different, we'll speak then in different terms. But what it is, basically, here's your definition of the dot product. We've got vector A dotted with vector B. That's not a multiplication in this case. This is a dot product. When you see vectors with a dot between them, that's a dot product, not a multiplication. It's related to multiplication, but it is not a multiplication. I'm going to show later in this video a little bit how they can kind of get an idea of what it is. So it's the length of A times the length of vector B times the cosine of the angle between them. And a couple of caveats here. Neither A nor B can be equal to 0. So we're talking about vectors of finite length. But now if one or both are 0, then you're going to get the dot product is equal to 0. And we're also going to see later on that if the two vectors are perpendicular, you get a dot product of 0. Now if we write the vectors in just the component format, where we just list the three x, y, and z components, and I've done this kind of in general because you can use different coordinate systems. So it's not strictly limited to the Cartesian coordinate system. Then the dot product of vector A and B is just the sum of the individual components, A1 times B1 plus A2 times B2 plus A3 times B3. So the dot product is a scalar. And just as the title is called a scalar, it's not a vector. Since in this video we're going to be looking at the cosine quite a bit, I wanted to just quickly go over just a little review of the cosine. So at 0 degrees, the cosine is 1. At 90 degrees, which is equivalent to pi over 2 in radians, it goes to 0. And then at 180 degrees, or pi radians, it goes to minus 1. So that's the range of the cosine we're interested in this on the dot product. Now let's look at this graphically. So here's going to be our vector A, and there's our vector B. And then there's our angle theta between them. Now what the dot product tells us, if we go through and do the basic math of that equation we were given, what we find out is that this dot product basically is just this length right here. It's related to that. So that's the length of A times the cosine of theta. So we're going to see that graphically that's what the dot product results in, that the way these two vectors are arranged. So that gives us a little more information. Next I want to look at 3 different cases just to give you an idea of what the dot product means. First, let's take it where here's our vectors A and B again, angle theta. The cosine of theta is greater than 0 because we're in that from 0 to 90 degrees. And that's for theta greater than 0 and less than 90, or pi over 2 radians. So in this case, A dot B, which is just the length of A times the length of B times the cosine of theta, is greater than 0. So that's our first case where theta is less than 90 degrees. Now let's look when the angle is 90 degrees. And there's our B vector, our A vector. And it's 90 degrees. In this case, the cosine of 90 degrees, as we just saw from the graph, is 0. Therefore, A dot B is equal to 0. So when they are perpendicular, that's the case that we get. Now let's look at when theta is greater than 90 degrees. There's B, there's A, that angle right there, theta. So theta is greater than 90 degrees, but it's going to be less than 180. So in this case, the cosine of theta is less than 0 because we're in the region between 90 and 180 degrees. So 90 less than theta, greater than theta. So it's in that region, which would be the second quadrant. So those are our three basic cases. It's going to be, in this case, it's going to be positive, 0, or negative. So A dot B is less than 0. So it's going to be negative. Now let's work an example. We want to find the inner product, the dot product, the scalar product, whatever you want to call it, the lengths and the angle between the two vectors. So here's going to be our vectors. A is 1, 2, 0. That's in component form. B is 3, minus 2, and 1. So we know that A dotted with B from that first equation we gave, where it's just the product of the components. So let's see, this is going to be 1 times 3. There's our first one. Plus the second one is 2 times minus 2. So that's 2 times minus 2. And then plus 0 times 1. So that's just going to be equal to 3 minus 4, which is equal to minus 1. So that is A dotted with B. That is the inner product right there. Now the problem has asked us to calculate more things, so let's do that. Let's calculate the length of A, and that is going to be equal to A dotted with itself. I didn't quite go over that in the initial definitions, but that's what it turns out to be. And you'll see it's just an application of the Pythagorean theorem, which is going to be equal to, so A is 1 squared plus 2 squared plus 0 squared. It's just these three components right here. There's the 1, and that's the squared. Now that is going to be equal to 1 plus 4 plus 0. It's just the root 5. So there is the length of our A vector. Now let's calculate the length of the B vector. B is equal to the square root of B dotted with itself. In this case, we have got 3 squared plus minus 2, quantity squared, plus 1 squared. So that's 9 plus 4, because the minus 2 squared is plus 4. So that's equal to the root of 14. So there is going to be our length of our B vector. Now from our definition of the dot product, we know that the cosine inverse A dotted with B divided by the length of A divided by length of B. We just took the inverse cosines of both sides of our definition of the dot product. Now that's going to be equal to, plugging these numbers in there, we're going to take the inverse cosine, and let's see, we have got minus 1 is the dot product, and then we've got the length of A is root 5, the length of B is 14, so theta is going to be equal to that number. Now, I'm going to put that in my calculator, and what I'm going to come up with is we want to find the cosine of minus 1 times evaluated at minus 11952. Now we're in our Desmos calculator, and we're going to calculate the cosine inverse. So let's get into the function keys, cosine inverse, and then what we have, let's go back in main. That is going to be minus, and then that is going to be a point. And then we have got 11952, enter. Okay, so that's going to give us 96.86 degrees. We can see we're in the degree function. Now we switch to the radian function. And that's going to give us 1.69 radians. So let's transfer that information from Desmos into this. So we're going to get theta is equal to 1.69 radians, or 96.8 degrees. So that is our angle. So that's the end of that example. Now what we want to look at is we want to look at some of the properties of the dot product. And I'm just going to give you these properties. First of all is the commutative property. And this results in right here, it's u dot v is equal to v dot u. The order doesn't matter, it's what that's telling us. Now if we take, in this case, a is just a constant times the vector b, and that quantity dotted with w, we can factor out the a, and it's just v times w. So that's the result of the commutative property. Now the distributive property tells us that u dotted with v plus w is just the same as u dotted with v plus u dotted with w. Now we have the non-zero property, and so what this tells us is the dot product of v times v is greater than 0, but it is equal to 0 if v is equal to 0. So we've seen that. I've got some, I'm not going to go into more examples here, but I do have a link at the description of this video where I have some other dot product examples. If you want to follow through with that and see how, I'm just going to work some numerical examples to give you more understanding of how this works. Hope you got something else video. If you did, like, subscribe. Thank you for watching.